Another type of acids and bases are the Lewis acids and the Lewis bases. Now, with these types of acids, by definition, Lewis acid is an acid that contains an electron deficient site. And that electron deficient site can be a hydrogen or can be a central atom that lacks electrons. Let's have an example of Lewis acids that contain an electron deficient site. All of these examples that you're seeing here, these are also examples of Bronsted and Lowry acids. We've talked about those to be Bronsted and Lowry acids. By definition, a Bronsted and Lowry acid is an acid that should have a hydrogen, and its hydrogen is electron deficient. These also are Lewis acids because this electron deficient hydrogen lacks electrons. So the definition here for the Lewis acid is that your electron deficient site should be there and it should be in desperate need of electrons. Whether it's a hydrogen or something else, it needs to be an electron deficient site in there so that the base with lone pairs can come and fill this electron deficient site with electrons. So Lewis acid should have an electron deficient site, and these are all examples of both Bronsted and Lowry acids and Lewis acids. Now, the opposite is not true. So we said that all the Bronsted and Lowry acids, because they have an electron deficient site, they are Lewis acids. But the opposite is not true because Lewis acids also can be acids with no hydrogen. And this is not the definition of Bronsted and Lowry acids. So if a Lewis acid doesn't contain a hydrogen, it should contain an electron deficient site. Let's have an example of these Lewis acids that contain an electron deficient site, which we target the central atom now. So you look at the central atom in there, and the central atom is not going to be octet. It's going to violate the octet rule. Like for example, BF3. Look at the central atom now. This type of acid doesn't have any hydrogen, so it is not considered to be a Bronsted and Lowry acid. But it is a Lewis acid because if you do the electronic configuration of the boron, you would see that its outermost shell is not completely filled. It has the p orbital, which is empty. So we can say that the boron is an electron deficient site. So this is going to be the electron deficient site, and we're going to represent it by E plus. E plus means that it is an electrophile. Okay, same thing for aluminum. Aluminum, do the electronic configuration, you're going to see that the p orbital is empty, so it's an electron deficient site. All of these, they can accept electrons from the base. Same thing goes with iron. Iron is a transition metal, but its outermost shell, the orbital, is not completely filled. It still have room for more electrons. So it's another example of a Bronsted and Lowry acid. Lewis bases, they follow the same definition as a Bronsted and Lowry bases. They should have electrons. This is why we say that all Lewis bases are Bronsted and Lowry bases. So these are the examples of the bases that we talked about, and all of these are bases from the nucleophilic site. So this is the nucleophilic site. So this is the base, and this is where the reaction starts. As in the Bronsted and Lowry bases, we mentioned about the double bond and the triple bond. So these are hidden source of electrons. After all, the pi bond is the overlap of two p orbitals. If I break this pi bond, then I'm going to release these two electrons, and those can be involved in bonding with electrophiles. The general reaction of the Lewis acid and the Lewis base is when Lewis bases react with Lewis acids. When they do that, because of the identity of the Lewis acid and because the Lewis acid lacks electrons, the base is going to donate its electrons, so it's going to generate or it's going to make a covalent bond, and it's going to make a complex. There are different cases in there involving a charged Lewis base or a neutral Lewis base, and a charged Lewis acid and a neutral Lewis acid. So the charge of the product is going to vary. Let's have a couple of examples in there. The following example. Aluminum chloride reacted with methanol. Whenever you have an organic reaction, you have to locate your nucleophile, which is the source of electron, and this is going to be the source of electron here, and your electron deficient site, which is the electrophile. And the aluminum is the electron deficient site, which is the electrophile. So the aluminum is the E plus, and the oxygen is our nucleophile. All the nucleophiles, since they are a source of electrons, the nucleophiles are bases. And methanol here, because it has lone pairs on the oxygen, it both follows the same definition for Bronson and Lowry base. So it can be either a Bronson and Lowry base or it can be Lewis base. Any one of those. Aluminum chloride is not a Bronson and Lowry acid. It's only a Lewis acid. So because it's only a Lewis acid, I'm going to choose the methanol to be a Lewis base so that I can carry out my reaction. And the reaction is going to happen as follows. Every time you have a Lewis base, your arrow is going to start from the lone pairs and it's going to go towards the electron deficient site. So it's the oxygen giving electrons to the aluminum. So oxygen in this case is going to lose electrons and aluminum is going to gain electrons. So I have to express this by a charge. I will make a bond between the aluminum and the oxygen. So let's go ahead and highlight the new bond that is made. So between the aluminum and the oxygen. Now the oxygen has on it the hydrogen and it has the CH3. So write all the groups that belong to the oxygen. So I'm going to have a hydrogen here. I'm going to have CH3. You can write them in any direction you want. I only used one lone pair on the oxygen to make the sigma bond. So I'm going to end up having the second lone pair in there. This is going to stay. And then on the aluminum, I still have my 3 chlorines. So I'm going to end up having a chlorine here, a chlorine here, and a chlorine there. However, you got to follow the direction of the arrow and see what element lost electrons and what element gained electrons. Oxygen lost a lone pair. It was a 0 charge. It lost a lone pair. So now it became 3 bonds and a lone pair. So now the oxygen is going to be a negative charge. Aluminum, on the other end, gained these 2 electrons from the oxygen by making a covalent bond. So aluminum is going to be a negative charge. And this is going to be a complex. This is an example of a neutral Lewis base reacting with a neutral Lewis acid. And you're going to end up getting a neutral product, but the product is going to be having ions in there that are adjacent to each other, but the sum of the ions have to be a 0 charge. We're still following the same rules of reactions. If your reactants are a 0 charge, then your product's going to be 0 charge as well. Let's have another example. Another example is in case I have a positive charge. So this is a solid positive charge on a carbon, and we call this a carbocation. And we're reacting this with sodium hydroxide. Okay. So this is going to be a positive charge. This is going to be a negative charge in there. Now, sodium hydroxide is an example of a base because it is a negative charge. So since it's a negative charge, this is a strong base. So this is going to be my nucleophile in this case. So always locate your nucleophile. Now, the electrophilic site is this carbon. This carbon lacks electrons. So the nucleophile can come and donate electrons, its electrons to this carbon here. This carbon lacks electrons, it doesn't have a hydrogen. So it's not considered to be a Bronson and Lowry acid. It's only a Lewis acid. So this guy is a Lewis acid, and it is my electrophile. So I located my nucleophile, I located my electrophile. My electrophile here is a charged. It is a positive charge. It's already in desperate need of electrons. And I have my base, which is fully charged because it is a negative charge there. So the base is going to lose electrons to give electrons to the positive carbon. So the base is going to lose electrons to give electrons to the electrophile. This is a reaction between a nucleophile, a charged nucleophile, and an electrophile. So what I did over here is I made a new bond. This is what I did. So I'm just going to draw the same backbone, but my reaction is going to be on this carbon. So on this carbon, I made a new bond, and that bond is going to be with the OH. I used only 2 lone pairs of the OH. I used just 1 lone pair, of the OH in there to make that sigma bond, but I have still the others, so go ahead and write them down. So whatever you did here, you made a bond between the oxygen and the carbon. Everything else stays exactly the same. Now let's go ahead and look at the charges in there. This carbon was already losing electrons. I gave it electrons, so it's now a 0 charge. This carbon, after all, has 4 bonds around it. Don't forget that when a carbon is positive, it needs to have 3 bonds around it. So this is the skeletal representation. However, you have hydrogen in here, and this hydrogen is still there. Okay, nothing happened to it. So this carbon has 4 bonds, so it's a 0 charge. This oxygen has 2 bonds and 2 lone pairs, so it is a 0 charge as well. So this is going to be my complex from the Lewis acid Lewis base reaction. Another example is whenever I have a double bond. So if I have a double bond here, this is a hidden source of electrons, okay, plus HBr. Now this example can be both Bronson and Lowry acid base reaction or Lewis acid Lewis base reaction. You choose, it doesn't matter, because this is a nucleophile here, and the source of my electrons is the double bond, and I have my hydrogen, which is partial positive because of the direction of polarization. So this hydrogen here follows the definition of Bronson and Lowry acid or Lewis acid. It is a Lewis acid because it has an electron or it is electron deficient, and it is a Bronson and Lowry acid because this acid starts with a hydrogen. So this is my base, and the base can be either a Lewis base or a Bronsted and Lowry base. You choose, but if you choose a Lewis base, then pick the HBr to be a Lewis acid and vice versa. Now, how the reaction is going to go, the reaction is always going to start from the source of electrons. And the source of electrons in this case is going to be my double bond. So the double bond here is going to open up and break. And when it breaks, it's going to come and give its 2 electrons to the hydrogen. Every time I make a bond, I break a bond, so bromine is going to leave. So I'm going to end up getting, here you go. Now on this carbon, I added my hydrogen, okay? I broke the double bond. This double bond was shared between those 2 carbons. This carbon got all the electrons. However, this carbon didn't get anything. So this carbon lost. To represent that, we have to put a plus sign. a positive sign in there. Plus, of course, my leaving group, which is a Br negative. Remember what I said before? The charges of the reactants, they should be exactly the same as the charges of the product. So if you have a zero reactants, zero charge reactants, then your product needs to be a zero charge. Here, the positive balances the negative charge of the bromine. Whenever you have a carbon with a plus charge, this is called a carbocation. Okay, we're going to be talking about carbocations in the next chapter, in a chapter 3. But there are different types of carbocations in there. I believe in the problem sets, I've talked about primary, secondary, and tertiary carbocations, but we will explain those in details in chapter